The implementation of 5S Lean tool using system dynamics approach. Abstract. The 5S sort, set, shine, standardize, and sustain Lean tool has been known to improve systems performance. In the current study, the short-run dynamic implications of sorting aspects of 5S is investigated using system dynamics. A system dynamics model is developed for manufacturing case study and simulated to establish the effect of sorting activity of manufacturing throughput. The purpose was to assess in advance the system performance outcomes when 5S practices are improved. The simulation results were the stimulus for real-life improvement in system because the simulation results were able to mimic real-life outcomes. While the simulation results encourage further improvements to be implemented, the model developed in the current paper is replicable in other instances as the variables used in the model are generic and common most types of manufacturing systems, particularly those new to Lean practices. The dynamic analysis of 5S Lean practices is not common. The study also reveals some interesting relationships between 5S and other Lean practices and between 5S and system performance. Contents: 1. Introduction. 2. System dynamics modeling. 3. Description of the problem. 4. Design and use of the system dynamics model. 5. Initiating an improved 5S strategy. 6. Study implications, conclusions, and future outlook. Introduction. Lean manufacturing comprises a set of tools and practices which, when implemented properly and fully, help to improve system performance. The 5S Lean tool is one of such. It is an acronym for sort, set in order, shine, standardize, and sustain. 5S helps to reduce non-value adding time, increase productivity, and improve quality. It has been used in the design of efficient facilities. 5S techniques have been integrated with other Lean tools to reduce changeover time. If Lean has not been firmly established in an organization, there is a tendency to go back to old ways of doing things. Lean practices that are meant to improve the system may be relegated in favor of ensuring goods are processed. In the current article, we describe a simulation-based methodology that enables the systematic implementation, improvement, and sustaining of 5S practices while also improving throughput for the manufacturing system. System Dynamics Modeling. System Dynamics (SD) is a methodology used for understanding the cause and effect relationships that exist in a system, such as manufacturing system. The simulation modeling aspects is intended to mimic a real-life situation, such the experiments undertaken in the model can give an idea about how the system will behave in reality and evolve over time when the experiments are actually implemented. SD has been used to investigate and improve productivity for a print shop, to forecast the performance of a home appliances manufacturer based on operational and financial measures, to investigate the dynamic performance of manufacturing cell under demand variability, to analyze the cost performance dynamics of production leveling in a manufacturing cell, to quantify the effect of Lean-based improvement options on the Lean time, and as a Lean assessment tool. Description of the problem. A typical problem in many small and medium-sized manufacturers is in variation of throughput due to a variety of reasons such as demand fluctuations and system inefficiency, for example, breakdowns and inaccurate set schedules. In the current article, the case of make-to-order print packing manufacturing system is presented. The company experiences seasonal demand and there are seasons of high and low demand. In low demand season, the system copes well and items are properly sorted and sorted in the right places. The plant is generally neat and tidy. The reverse is the case in high demand periods. The plant managers are overwhelmed and more concerned with meeting customer delivery due dates than with maintaining a well-arranged plant. The situation is firefighting approach to Lean implementation until the high demand season ends. The methodology describing the use of SD to improve the 5S implementation. Describe the problem and define the key issues relating to 5S and how they impact the system performance. Design the SD model that captures the dynamics of the key issues. Validate the SD model, set apart key improvements, and simulate their effect on the system performance. Use the simulation results to justify the extent of improvements in 5S practices. Implement the improvements. For the feedback purposes, compare the real life with the simulation results. Design and use of the system dynamics model. Design of the SD model. The dynamics behind the model is straightforward. Manufacturing lead time is measured against the target level. The higher the gap, the more pressure to attempt to reduce the gap. The higher the pressure to reduce the manufacturing lead time gap, the more the managers and employees cut corners by spending less time doing things that they believe will not directly increase the throughput. The governing equations of the SD model. Governing equations are used to define the relationships between the cause and effect variables. The equations enable the SD model to be simulated. Validation of an experimentation with the SD model. The SD was simulated for a period of 30 days. 3 variables in the SD have been set apart for further analysis: throughput, time used in finding, and lead time. Throughput. The SD simulation results show that throughput increases slightly in the first few days before dropping. The increase in throughput at inception is a result of the improved efficiency level in sorting, which provides a starting boost to the system before it is loaded with more jobs orders. The rate of drop in throughput is not as significant when compared with the current as is. On the 30th day, the throughput is about 26.5 completed orders per day when compared to less than 24 completed orders for the current SS. This is an improvement of 10% over the present situation. Time used in finding. The total time spent looking for items reduces from 0.6 to about 0.2 work hours per day. This is a 67% improvement in time spent looking for items. With these savings, workers can have more time doing more value-adding activities, while time spent in setup and repair activities decreases. Lead time. Manufacturing lead time is affected by time-related losses along the various processes. With the time saved in setup and repair, machine idle and stoppage time is reduced, whereas manufacturing lead time is reduced when throughput is increased. The improvements in throughput and time spent looking for items which have been achieved with the improvement in normal sort time have had a positive impact on manufacturing lead time, which has improved by 33% at the end of the simulation run. Initiating an improved 5S strategy. All the improvements took approximately 2 weeks to implement. Since shelves were already in place, there were no major cost outlays. In order to attribute changes in throughput performance to change in sorting behaviors, all other variables in the system were held constant as best as possible. After the 2-week implementation, a study was conducted to establish the overall improvement in the average sort time and system throughput. The real-life results were compared to the simulation results. The time saving achieved by improving the sorting activities was used to reduce the additional man-hours that is often required when workload rises during the onset of the high-demand season. Study implications, conclusions, and future outlook. The SD model was built and simulated to indicate how system throughput will improve as 5S practices are improved. The methodology advanced and used in the present study has shown that direct and unambiguous link between improvement in 5S and the impact on manufacturing system performance. While the methodology shows throughput improvements, it also shows improvements in other aspects of the system. For example, the impact of the sorting lean practice can be seen in other lean practices such as time used in setup and repair activities, two important aspects of just-in-time management and total productive maintenance. The simulation encouraged the company's managers to adopt the methodology to improve other aspects of Lean using a SD modeling technique. It would be worthwhile to investigate a wider range of Lean practices as well as their long-term dynamic effects. Here you can observe the shelf arrangement A before 5S improvement and B the shelf arrangement after the 5S improvement.